Section: Introduction. In this section, we discuss few-shot chain of thought, COT, prompting, which has proven to be a powerful method for improving the reasoning abilities of large language models, LLMs. By providing a few examples of step-by-step reasoning during inference, the model can apply this reasoning to new tasks, leading to better performance in complex problem-solving, especially in areas like math and common-sense reasoning. We note that there are two main approaches in the literature for analyzing how transformers handle COT tasks. The first involves explicitly building a transformer by defining its parameters and assigning tasks to its components. The second approach organizes reasoning steps into a specific data format and trains a transformer to learn this step-by-step prediction process. Previous studies using these methods have shed light on the transformer's capabilities in COT tasks and how its components contribute to multi-step reasoning. However, a significant limitation of these analyses is that they often ignore the connections between multiple reasoning steps. In the first approach, predictions at each step rely only on the previous step's result. Similarly, in the second approach, a filtering process is used to focus only on the most recent step, which means earlier reasoning steps are not considered. We refer to this limited prediction process as stepwise ICL. In contrast, in real-world scenarios like next token prediction, the LLM considers all previous tokens, which we call coherent COT. Recognizing the difference between stepwise ICL and coherent COT, we expand the theoretical framework to study the properties of a model trained with coherent COT and compare it to one trained with stepwise ICL. Our findings suggest that training with coherent COT leads to better prediction performance. This is because treating COT as a complete process allows the transformer to account for potential errors in earlier predictions, leading to self-correction and improved outcomes. While coherent COT may outperform stepwise ICL, it requires training on the entire reasoning chain, which can change the model's optimal parameters and behavior. This raises questions about which steps in the reasoning chain are most error-prone, highlighting the need for sensitivity analysis. Our second contribution focuses on how the trained coherent COT model responds to changes in the demonstration examples during inference. We find that the model is more sensitive to noise in the intermediate reasoning steps than to errors in the final outcomes. Inspired by this sensitivity analysis, our third contribution is a method for composing prompts to enhance COT performance during inference. Since COT is particularly sensitive to inaccuracies in intermediate steps, improving the accuracy of these steps can boost overall performance. We propose including both correct and incorrect reasoning paths in demonstrations to enhance the accuracy of these intermediate steps, and we conduct experiments to validate the effectiveness of this approach. In the related work section, we highlight that COT prompting has been shown to significantly improve LLM reasoning by breaking down complex tasks into manageable steps. Various extensions of COT, such as zero-shot COT and tree of thought, have emerged to further enhance efficiency and performance. Recent studies have also explored the mechanisms behind COT, revealing that maintaining attention on relevant tokens and the correct ordering of reasoning steps are crucial for its effectiveness. Additionally, it has been found that simpler tasks require fewer reasoning steps, while more complex tasks benefit from more detailed inference sequences. Section Summary. In this section, we discuss the effectiveness of few-shot chain of thought, COT, prompting in enhancing the reasoning capabilities of large language models, LLMs, and explore two main approaches for analyzing transformers in COT tasks. We highlight the limitations of existing methods that treat reasoning steps in isolation and propose a coherent COT approach, which integrates earlier reasoning steps for improved prediction performance, while also addressing the model's sensitivity to perturbations in intermediate reasoning steps and suggesting a prompt composing method to enhance overall COT performance. Section: Theories in ICL and COT. In this section, we explore the theories behind in-context learning, ICL, and chain of thought, COT. The mechanism of ICL has been thoroughly examined in theoretical studies. For instance, some research has shown how ICL can learn linear regression through gradient descent. Other studies have expanded on this by looking at how transformers can use ICL for nonlinear functions, while some focus on generalized linear models, ridge regression, and lasso. Additionally, it has been noted that multi-head attention is preferred over single-head attention in ICL tasks. Beyond ICL, recent work has begun to create theoretical frameworks for understanding COT. For example, one framework views COT as a series of ICL components that tackle smaller subproblems. Another study has developed a transformer that addresses arithmetic and linear equation tasks using COT. There is also a Bayesian perspective that explains how intermediate steps enhance reasoning. Furthermore, a theoretical upper limit for the expressiveness of constant precision transformers has been established, along with a hierarchical graphical model that illustrates how large language models generate sequences of reasoning steps. We extend the existing theory of ICL and transformers to a COT context for our theoretical investigation. We make two key observations. First, using coherent COT during training leads to better inference performance compared to stepwise ICL. Second, when there is noise in the demonstration examples during inference, models using coherent COT are more affected by changes in reasoning steps than by inaccuracies in the final output. Next, we outline our data generation process and transformer architecture, followed by our theoretical results. In our data generation process, we define how examples and query data are created. Each prompt includes examples and query data that are independently and identically distributed, sampled from a two-layer, noisy regression model. The independent variable is drawn from a normal distribution. The intermediate response is a linear combination of this variable, and the final response includes some noise. All examples and query data in a prompt share the same parameters, which are sampled uniformly from a unit sphere across different prompts. We define coherent COT and stepwise ICL as follows. Stepwise ICL involves two separate steps, each handled by a different model. The first model predicts the intermediate response, and the second model uses this response to make the final prediction. In contrast, coherent COT integrates the intermediate response into the input for the second step, allowing it to utilize both the intermediate reasoning and the original inputs for the final prediction. While some literature suggests relaxing the structured data format assumption, we observe that ICL's performance with structured data sets a lower bound for optimal performance. The main distinction between coherent COT and stepwise ICL is that the latter only includes intermediate and final responses in the second step, while coherent COT incorporates the predicted intermediate response back into the original input, enhancing its predictive capability. Section Summary. In this section, we explore the theoretical foundations of in-context learning, ICL, and chain of thought, COT, in transformers, highlighting how coherent COT outperforms stepwise ICL in inference performance and sensitivity to noise. We also define the data generation process for our experiments and differentiate between coherent COT and stepwise ICL, emphasizing the advantages of integrating intermediate responses into the final prediction process. Section: Model Architecture. In this section, we describe our model architecture, which is based on transformers featuring a single-head linear attention layer. We define the input prompt as E, with matrices for key, query, and value represented as W_Q, W_K, and W_V, respectively. The output layer is denoted as W_out. For our first function in stepwise ICL, we set the size of these matrices to D+1, while for the second function, we use a size of 2. In the case of coherent COT, the size is D+2. To train our model for both stepwise ICL and coherent COT, we aim to minimize the mean squared error between the predicted response and the true response of the query example. Here, theta represents the parameters of the transformer. We then compare coherent COT and stepwise ICL. To simplify our analysis, we assume specific formats for the attention parameters. For stepwise ICL, we define the parameters of our first function, where the product of the key and query matrices has a specific structure, and the output layer's corresponding row is defined. For the second function, we have a similar structure with different values. In coherent COT, we assume a more complex structure for the key and query matrices and define the output layer's rows accordingly. Based on our observations, we rewrite the loss function to focus on the parameters relevant to each method. We find that the optimal expected loss for stepwise ICL occurs under certain conditions, leading to a specific expression for the loss. We also note that if we relax our assumptions to other distributions, we lose the ability to derive a closed-form expression for comparison. Despite this, we maintain that coherent COT generally outperforms stepwise ICL because it retains more information from previous reasoning steps. We derive the optimal solution for coherent COT, showing that its parameters must satisfy specific relationships to minimize loss. We further analyze how the parameters influence the final prediction. We find that in coherent COT, the initial inputs positively contribute to the final prediction, and the model relies less on intermediate values compared to stepwise ICL. This reduced dependency allows coherent COT to better adjust predictions when there are errors in intermediate steps. Finally, we conduct simulations to validate our theoretical findings. We train transformers from scratch using data generated under our assumptions. By separately training the models involved in stepwise ICL, we ensure stable convergence. Our results show that as the number of examples increases, coherent COT consistently achieves lower error rates than stepwise ICL, confirming its superior predictive performance. Section Summary. In this section, we describe our model architecture based on transformers with a single-head linear attention layer and outline our training objectives, which minimize the mean squared error between predicted and true responses. We compare the performance of coherent COT and stepwise ICL, demonstrating that coherent COT consistently achieves lower expected loss and better prediction accuracy due to its reduced reliance on intermediate values, allowing for effective self-correction in the presence of errors. Section: Sensitivity against random perturbation. In this section, we examine how coherent COT performs better in predictions compared to stepwise ICL by considering all previous reasoning steps. However, this comprehensive approach may also affect how sensitive the model is to errors or disruptions at each step. We investigate this sensitivity by analyzing the impact of random changes at different reasoning stages, specifically at points we refer to as y, x, and z during inference. We denote the loss for coherent COT when random noise is added to y as L for y. When we optimize the values for x, y, and z, we find that as the number of examples increases, the additional loss from noise in y decreases significantly. This indicates that noise in y has a minimal effect on COT's performance. Next, we explore the effects of random noise added to x. We also analyze the expected loss when noise is introduced to z. The proofs for these findings are similar to the previous theorem and can be found in the appendix. Our results show that when we introduce random noise, whether to x or z, it generally leads to a higher expected loss compared to noise in y. Specifically, we find that errors in the reasoning steps, x and z, have a more significant impact on the final prediction accuracy than noise in the final label, y. This suggests that we should focus more on potential errors during the reasoning process rather than just on label noise. We also present simulation results that illustrate COT's sensitivity to random changes at different reasoning steps. Our setup mirrors previous experiments, with a noise variance set to 1. The results indicate that when noise is added to y, the loss remains low, but when noise affects x or z, the loss increases considerably. This aligns with our theoretical insights, confirming that COT is more affected by perturbations in earlier reasoning steps than by noise in the final output. Section Summary. In this section, we investigate the sensitivity of the coherent COT model to random perturbations at different reasoning steps, finding that errors in the intermediate steps, x_i and z_i, significantly impact performance more than noise in the final label, y_i. Our simulations confirm that while perturbations to y_i have minimal effect, those to x_i and z_i lead to a notable increase in loss, highlighting the importance of addressing errors during the reasoning process. Section: Improving COT through error-aware demonstrations. In this section, we analyze how the chain of thought, COT, method is affected by errors during reasoning. We find that COT is more impacted by mistakes in the reasoning steps than by errors in the final answer. This leads us to believe that it is helpful for the model to learn to adjust its predictions by recognizing earlier mistakes. Therefore, we suggest including both correct and incorrect reasoning paths in COT demonstrations. To illustrate our method, we use a date understanding problem and present our demonstration format. In standard COT prompting, we typically provide examples with correct reasoning. However, in our approach, we first show a potentially incorrect reasoning path, clearly marked as wrong, followed by an explanation of the errors in that reasoning. We manually create both the incorrect reasoning and the analysis of its flaws. After this, we present a step-by-step correct reasoning process that leads to the right answer. By including both types of reasoning, we teach the model not only the correct path but also how to identify and manage potential errors, enhancing its overall reasoning performance. Next, we evaluate our method using various large language models, LLMs, across multiple benchmarks. Our experiments involve 4 LLMs: GPT 3.5 Turbo, GPT 4o Mini, Gemini Pro, and DeepSeek 67B, with a temperature setting of 0 for consistent outputs. We utilize 5 datasets from 2 benchmarks: the BBH benchmark, which focuses on reasoning tasks, and the GSM-8K benchmark, which includes arithmetic and grade school math problems. Our results show that incorporating incorrect reasoning paths generally improves model performance. For instance, in the Tracking Shuffled Objects dataset, Gemini Pro improves by 6.60%, and DeepSeek 67B increases by 6.17% in the Penguins in a Table dataset. These findings emphasize the benefits of exposing models to incorrect reasoning paths. We also conduct an ablation study to assess the importance of including error explanations. When we provide only the incorrect reasoning path without an explanation, we find that performance often decreases. In some cases, like the date understanding dataset, the results are worse than when no incorrect reasoning is provided at all. This suggests that simply showing incorrect reasoning without explaining the errors can confuse the model. Additionally, we explore using model-generated incorrect reasoning paths instead of handcrafted ones. While creating incorrect paths manually is efficient, using model-generated paths may enhance learning since the model can better recognize its own mistakes. We still provide manual explanations for these errors. Our results indicate that model-generated incorrect paths often lead to better performance, with DeepSeek 67B showing a significant improvement from 82.88% to 88.36%. This suggests that allowing models to learn from their own errors can strengthen their reasoning abilities. Finally, we note that the results for the standard COT case differ from those with incorrect reasoning paths due to variations in the example questions used. This highlights the importance of selecting appropriate examples in COT demonstrations.